Hello there, Mr. Sutton here, bringing you the AB Calculus 4-8 Extra Practice Number 1 Solutions on Mean Value Theorem. For this problem, I'm trying to figure out x values on the interval from -4 to 6 that satisfy the mean value theorem for x squared plus x. So essentially I'm asking, if I find the average rate of change for this function over this interval, at what x values does the instantaneous rate of change come out to the same thing? Before I can do any of this, though, I need to make sure the mean value theorem applies. So for that to apply, our function needs to be both continuous and differentiable, continuous on the closed interval from -4 to 6, and differentiable on the open interval from -4 to 6. This is a polynomial, so it is continuous and differentiable everywhere, including this interval. So let's go ahead with our number crunching then. So let's do the average rate of change first. For that, I need f of 6 minus f of -4 over 6 minus -4, or 6 plus 4. F of 6, that's going to be 36 plus 6, which is 42. F of -4, we've got 16 minus 4, which is 12. So we've got 42 minus 12 over 10. So that's going to be, let's see, 30 over 10, which is 3. And the reason I'm bothering to simplify this is I'm going to need to figure out where f prime equals 3. So I might as well simplify it now because I'm going to have to do it later anyway. So f prime then, I rock, that's going to be 2x plus 1. And that equals 3 at what x values? Well, if you subtract 1 and divide by 2, you got x equals 1. And just double checking real quick, 1 falls strictly between -4 and 6, so that's an acceptable value. For this problem, we're trying to find all x values on the interval 0 to 3 that satisfy mean value theorem, in other words, a rock equals I rock, for this radical x plus 1 function. Before we do any number crunching, let's make sure the MVT applies here. So the only discontinuities we have to worry about here are places that make the radical negative inside. So if you have an x value that's less than -1, you're going to square root a negative, and that's going to be bad for continuity, differentiability, and really just the function existing at all. However, for all x values that are greater than -1, your function is going to be continuous and differentiable. And we can have a debate about, what happens if x is exactly -1 for continuity and differentiability, but we don't really need to worry about that because the interval 0 to 3 doesn't even include that border value of -1. All right, so let's go ahead and do a rock and I rock. For the average rate of change, we've got f of 3 minus f of 0 over 3 minus 0. F of 3, that's going to be square root of 4, which is 2. F of 0 is square root of 1, which is 1. So you've got 2 minus 1. So that's going to be then 1 over 3. Now we need the instantaneous rate of change. We need a formula for f prime to start with. So that's going to be 1/2 times x plus 1 to the -1/2 power. And we've got a tail of 1 that we don't have to worry about there. So let's set that equal to a rock now, to 1/3, and solve for x. So first step to solving, let's get rid of this 1/2 out here by multiplying both sides by 2. So that'll be 2/3 over on the right side. Now let's get rid of this exponent by raising both sides to the -2 power, the reciprocal power. That gives us just x plus 1 on the left and 2/3 to the -2 on the right side. If I'm raising this to the -2, that's really like having 3 over 2 to the +2 power. So that's going to be 9 over 4 when the dust settles. And then subtracting 1, you're really subtracting 4/4 to get 5/4. Now, is 5/4 on the interval from 0 to 3? Strictly between 0 and 3. It is. So therefore, we're going to just keep this answer and be on our merry way. For this no calculator problem, we're given a function such that f of 0 is 1 over pi squared and f of 2 is, well, the same thing. And our derivative is this function right here. Based off of this, how many values on the interval from 0 to 2 satisfy the conclusion of the mean value theorem for the function on the closed interval from 0 to 2? All right. So first off, if we're asking how many places does the MVT get satisfied, well, maybe we should ask if the mean value theorem even applies at all. So we need continuity and differentiability on the interval from 0 to 2. For the continuity piece of it, I mean, you have a polynomial, which is continuous, times a trig function, a cosine function, which is also continuous. They're also both differentiable. So the product of these is going to give you something that is both continuous and differentiable. So we keep going, and let's find the average rate of change. We've got f of 2 minus f of 0 over 2 minus 0. So if we're looking for where the a rock equals I rock, our a rock then, we've essentially got 1 over pi squared minus 1 over pi squared over 2 minus 0. That's just 0 over something that's not 0. So that's just 0 for the average rate of change. Now we need to figure out where f prime equals that. So let's go ahead now and solve for x in this situation. Now this is a little bit tricky, but it's already factored, so you can actually say right away that x equals -1 would solve this equation, because that would zero everything out. The trouble is, -1 is not between 0 and 2. So that's just kind of out of bounds, doesn't count. Moving on then, we want to know where cosine of pi x equals 0. And this is where it helps if you know that cosine in general equals 0. The x value on the unit circle equals 0 at the top and the bottom of the unit circle, at pi over 2 and 3 pi over 2. But we could actually keep going, right? Because there's 5 pi over 2, 7 pi over 2. So there's a long list of values where cosine equals 0, which means that pi x equals all those things. So how do we get x? Well, we have to divide by pi. If I do that, I've got 1 over 2, 3 over 2, 5 over 2, and so on and so forth. But now we're asking about the interval from 0 to 2. And there's only two values on that interval here, 1/2 and 3/2. So that means for my answer choice, it's going to be choice C, 2 values. For this one, if f is a continuous function on a closed interval, which of the following must be true? So whenever you see continuity in closed interval, we start thinking about different theorems. We had the intermediate value theorem, the extreme value theorem, and the mean value theorem that all require this as one of the only condition or possibly one of a few conditions. So let's look at these answer choices now. First one, there is a number c in the open interval from a to b, so in other words an x value, such that the y value there, f of c, equals 0. So they're saying if we have a continuous function on a closed interval, we're guaranteed that it has the y value 0 somewhere in there. Now that's definitely not guaranteed. We can think of lots of continuous functions that never cross the x-axis. The simplest one I can think of is the horizontal line y equals 1. Definitely continuous, but does not cross the x-axis anywhere. So choice A can't be true for everything. Choice B, there's a number c such that f of A less than f of c less than f of b. So basically they're saying, you're guaranteed that the y value somewhere in there is going to fall strictly between the beginning y value and the ending y value. But what if the beginning and the ending y value are exactly the same? There's nothing they wrote here that precludes that. So this is also going to be false. And again, consider the function y equals 1. I mean, it's continuous, it's on a closed interval, and yet there's no way that this is strictly between any numbers because it's the same value everywhere. All right, moving on. We've got a c value such that f of c greater than or equal to f of x. So they're basically saying that there's a y value somewhere on my function on this closed interval such that that y value is bigger or the same as all the other y values. And this is actually going to be true by the extreme value theorem. Says if you have a continuous function on a closed interval, you're guaranteed there's an absolute max and an absolute min. Now the absolute max doesn't have to be bigger than all the numbers, it just has to be at least as big as all the numbers. And they put the equals in here, so they covered their bases there. So this looks like a pretty good answer choice, but let's look at the others just to be on the safe side. So choice D, there's a c value such that f prime of c equals 0, basically saying we're guaranteed to have a slope of 0 somewhere on our interval if it's continuous. And that's not necessarily true. There are continuous functions that never have a slope of 0, such as the line y equals x. That has a slope of 1 everywhere, but again, it is continuous. Let's look at the last one now. There's a C value such that f prime of C equals f of b minus f of a over b minus a. This is essentially saying that I rock equals a rock. And this is going to be true if you also have the function being differentiable on the interval from a to b. The MVT, which is what this is, mean value theorem, also requires differentiability. But they didn't say it was differentiable. They just said it was continuous. So we don't have enough information for E either. So that means that choice C then is the only one we can pick. For this problem, we're given a table of the f function here, which we're told is differentiable. And we're also told f and its derivative, f prime, are strictly increasing between 0 and 5. So based off of that, we want to know which of the following could be a value of f prime of 3. So we don't really know what the f function does other than what we have in the table here. But in order to figure out what could be a value, we kind of need a lower bound and an upper bound for what f prime of 3 could be. So to approximate these lower and upper bounds, we're going to use the average rate of change from the table values here. I know that f prime of 3 has to be between the average rate of change between 2.8 and 3 and between 3.1 and 3 and 3.1. It has to be because they told us this was a strictly increasing function. That means whatever the average from here to here is, and the average from here to here, the instant slope at 3.0 is going to be between those things because we're always increasing. So let's find the average rate of change for this first set of numbers. That's going to be 45 minus 39.2 over 3.0 minus 2.8. And we're saying that is strictly less than f prime of 3. And then f prime of 3 has to be strictly less than 48.05 minus 45 over 3.1 minus 3.0, the a rock between 3.0 and 3.1. And this is a calculator question, so let me just calculate those. So our lower bound then is going to be 29, and let me now plug in this upper bound set of numbers, and that comes out to 30.5. So f prime must be between 29 and 30.5. And hey, look, 29 and 30.5 are actual answer choices, so it's important that this was less than and not less than or equals to. The only number strictly between these numbers that they gave us is 30, so choice D. For this problem, a portion of a graph differentiable of the differentiable function f is shown above. If the C value 3 satisfies the conclusion of the mean value theorem applied to f on this interval, what's the slope of the line tangent to the graph at x equals 3? So just to review what the mean value theorem says about this situation is that the instantaneous rate of change at x equals 3 equals the average rate of change on the interval from -2 to 8. That is what the mean value theorem is telling us about this situation if 3 actually satisfies the conclusion to the mean value theorem. Okay, so we want to find the slope of the tangent line. We just need to find the average rate of change from -2 to 8 because that's going to match the I rock that satisfies that conclusion. So we've got, let's see, -3 minus 5 over 8 minus -2. So that's going to be -8 over 10, which is going to come out to -4/5 if we reduce that, which we have to because the answer choices did. So that's going to be answer choice C. For this problem, I have a function defined by f of x equals 3x minus 4 cosine 2x plus 1, and they gave us the derivative pretty much for free. We could have come up with it on our own, but whatever. We want to know all values of x that satisfy the mean value theorem on the interval from -1 to 2. All right, so we're essentially asking where does the average rate of change of the f function over the interval -1 to 2, where does that equal the instantaneous rate of change of the function on this interval? So we need to find the average rate of change and basically set that equal to the instantaneous rate of change and see where things match up. So average rate of change, we're going to have f of 2 minus f of 1 over 2 minus -1. And I'm just going to put that directly into my calculator. So I'm going to put this f of x in my y equals and just use that here to get the most accurate number. So here's what I've entered in my y equals on my calculator. In y1, I have my f of x function that I'm going to plug some things into now. In y2, I've also actually entered my derivative function because I am going to need to figure out where this equals whatever constant we get out of this mess. So I'm going to need that to graph for later on. All right. So quitting back to the main screen, I did my little fancy fraction, and I'm doing, this is essentially f of 2 minus f of negative 1 over 2 minus negative 1, which is just 3. It comes out to 3.3422 if we round it off. Now I'm going to be needing this value later on, and I want to store it and get as accurate a number as possible. So I'm going to use the store function, and I'm going to make that alpha a, or whatever letter you want to store it as. Now I can call it up whenever I want. Okay, so at this point, I'm going to set the f prime, which they already defined for me, equal to this number that I just got, and I'm going to figure out where those line up on the calculator. So back on my calculator now, I'm going to go into my y equals, and I'm going to create a y3 here. In y3, I just want to graph a horizontal line corresponding to this number. And to get as accurate an answer as possible, I'm going to do alpha a, and I'm going to put in that stored constant. Now I need to graph these. Where should I graph them? Well, they're asking about the interval -1 to 2. So I'm going to go to Window, and I'm going to make sure I'm graphing between -1 and 2 for the x values. Then I'll do zoom 0, zoom fit, and that should hopefully give me a window where all the things I want to see are coming together and accurately represented. All right, so the curvy thing here was our f prime. This horizontal line that we drew, that was this constant. We just need to see the x values where those intersect, because that's telling us the places where A rock and I rock match up. So I'm going to go to second trace, and I'm going to select option 5, intersect. And let's see, where's my little spider? There it is. I'm just going to press enter 3 times, once for the first curve, once for the second curve, once for the whatever. And that gives me 1.049 for one intersection, which is in one of the answer choices. Let's just find the other intersection just for the sake of doing it, although we probably have enough to pick an answer choice. So I'm going to move over to my other intersection point right there. And that also gives me a number, -0.479. So I had 2 intersection points, one at -0.479, one at 1.049, and that's enough to choose answer choice B. For this problem, we're actually going to be using this table for a set of problems. We've got a twice differentiable set of functions, f and g, and their values and their derivative values are given at various places in this table. Part A here, we want to find the x-coordinate of each relative min of f on the interval -2 to 3. Justify your answers. So we don't know anything about f double prime. We only have f prime. So we're going to be looking at the first derivative test here. If we want relative mins, we're looking for places where f prime changes from negative to positive. So here's my f prime row, and I'm looking for a negative to positive change. Well, we go negative to negative at -1, so that's no good. We go negative to positive at x equals 0. So that's the only place we can be sure about having a relative min on this graph. Okay, so that means that we're going to have a relative min at x equals 1 because f prime changes there from negative to positive. That's what you have to write, or something along those lines, to justify your answer on this one. For this problem, we're being asked to explain why there must be a c value between -1 and 1 such that f double prime of c is 0. So we didn't really get told a whole lot about f double prime other than the fact that our f function is twice differentiable. So we know that f double prime exists, but beyond that we don't know much. So we're going to have to get some information about f double prime by looking at the next best thing, f prime. Now, f double prime is the instantaneous rate of change, the IROC, for f prime. And we can make conclusions about what the instantaneous rate of change needs to be for a function if we know a little bit about the average rate of change of the function. The mean value theorem says if we have differentiability on an interval, then the AROC for that interval and the IROC somewhere on that interval are going to match up. So let's start by talking about the average rate of change for f prime. And that'll tell us a little bit about the derivative of f prime. So between -1 and 1, which is the interval they're talking about, we're going from 0 to 0 for f prime. That means you're going to have an average rate of change of 0. So your average rate of change of f prime on -1 to 1 is 0. To go from 0 to 0, you have to have had an average slope of 0. Okay, so since the average rate of change is 0, and since f prime is differentiable, they told us f was twice differentiable here, so that means f prime has its own derivative. That means the mean value theorem guarantees there's an x value between -1 and 1 that has an IROC, which is what f double prime is, of 0. So we're just using mean value theorem to show that the derivative of f prime is 0 somewhere between -1 and 1. For this problem, we have this h function that comes out of nowhere, and this is being defined as the ln of f of x. Based off of this, we just want to find h prime of 3. Okay, well, that means we have to take the derivative of ln of f of x. So derivative of ln, which is the outer function, that's going to be 1 over the inner function, so 1 over f of x. But then we have to multiply by the derivative of the inner function, which is f prime. So we have 1 over f of x times f prime of x. I'm just going to shorten that to be f prime of x over f of x. Just move it all into one big fraction. So if I want h prime of 3, I really need f prime of 3 over f of 3. Okay, well, those are things I can look up in my table. F prime of 3 is right here. It's 1/2. F of 3 is right above it. That's 7. So we just really have 1/2 over 7. Once you've written this, you're done. You could simplify it, but you do so at your own risk. If you do simplify it and drop that 2 down there or multiply by 1/7, either way, you end up with 1/14.